In a distributed system, if every server knows the protocol, and even more, if the protocol is deterministic, do the servers really need to send every single message? No, they don't. Instead, they could try the approach we present today, embedding a deterministic Byzantine fault-tolerant protocol in a block DAG. I'm Maria Schett, and this is joint work with George Denasis. We are both from University College London. So what is our system model? We have a distributed system with Byzantine servers. Those behave arbitrarily. Then we have the familiar constraint of 3f plus 1 servers to tolerate at most f Byzantine ones. Our links are asynchronous with one assumption. If a correct server sends something to another correct server, then what was sent is received eventually. Our servers build a block DAG together. What is a block DAG? A block DAG is like a blockchain. So a chain of cryptographically linked blocks. But instead of a chain, we have now a directed acyclic graph. So a block DAG is a DAG where the vertices are cryptographically linked blocks. So what is the background of our work? On the one hand, we have block DAG-based blockchains. We have Hashgraph, we have Aleph, we have Blockmania, and Flare. They report impressive efficiency gains by using a block DAG, and some even have commercial applications. Two recent academic works leverage block DAGs too. DAGrider, which is presenting at this conference too, and Narwhal and Task. So what's the pedigree? The idea to replay our deterministic protocol is from the system peer review. And finally, block DAGs essentially encode Lampert's happened before relation. In our work, we have two core ideas. So, first, idea 1, every correct server builds a joint block DAG. Then, through this joint block DAG, every correct server, idea 2, can interpret a deterministic fault-tolerant protocol P locally. We go through these two ideas now. So, we first look at how we build a joint block DAG. We see a simplified block DAG arranged in a grid. We have two servers, S1 and S2. The blocks on the first row are created by S1. The blocks on the second row are created by S2. The servers built the joint block DAG with the gossip protocol. There, the servers continually exchange blocks. Eventually, they will both see the same joint block DAG. So, what is inside such a block? First, the creator of the block. So here it is S2. The creator assigns the block so every other server can check the block was indeed created by S2. Then there is the reference to one parent block. A parent block is a dedicated block by the same creator. Essentially, we have a chain here. Only one parent per block. Then we have references to predecessor blocks. These references create the graph structure. They are the links. Because they are cryptographic hashes, no Byzantine server can introduce a cycle between blocks. Hence, our block DAG remains a DAG. So S2, if it's correct, will only insert a valid block. And a block is valid if it is signed by its creator, it has exactly one parent or none, and S2 considers all predecessor blocks valid. The last condition guarantees that S2 has seen and checked all predecessor blocks. Validity can be checked locally by S2 and every other server. Finally, a block has user requests. These are directly described into the block. We will come to them in a concrete example. So, to recap, a block DAG tells when which block was received for every server to every server. And because of this, I think of a block DAG also as a log DAG. Now we look at this same block DAG and interpret a protocol on it. So we look at the second idea. So we want to interpret P as reliable broadcast. Recall that user requests were written directly into the block. We here show the user request R in the first block. I also gave numbers to the blocks to reference them. So block 1 is parent to block 2 and a predecessor of block 3, and block 3 is a predecessor of block 4. Next, we interpret the protocol embedded in the block DAG. That is, we simulate the run of the protocol for every server. We can do this completely independently from the gossip protocol. Because the servers will eventually have the same block DAG, they can do this locally and will arrive at the same result. So we want to interpret reliable broadcast. The user requests broadcast R for block 1. So we interpret block 1 as if S1 sent the message echo R to start the reliable broadcast. Then we interpret block 2. In block 2 we simulate that S1 receives echo R from block 1. Now, S1 doesn't really receive this message from the network. We interpret the link from block 1 to block 2 as S1 receiving all messages from block 1. With the same reasoning, in block 3, server S2 receives echo R from the link from block 1. Now, in the real broadcast protocol, both S1 and S2 at this stage now echo R. And so we interpret block 2 and block 3 as if S1 and S2 send echo R. Now we interpret block 4. Let's assume that S1 and S2 is a quorum. That means at block 4, S2 received echo R from a quorum through block 2 and block 3. So according to the reliable broadcast, S2 now sends ready R. And so it goes on. This is how we interpret the protocol. But the messages were never sent. We just interpreted the graph structure. With a deterministic protocol, we know what every server does next. We can just simulate the run of the protocol. The only message that cannot be inferred from the edges is R. So they are written in the block. But we can infer all the other messages because our protocol is deterministic. We can simulate the next step of every server without ever sending messages. So this is the first major advantage of our block DAG approach. All the messages in yellow were never sent. We have message compression to the point of omission. Now, this is not the only advantage. Every other block also has requests in there. For example, block 3. It has some request R2. So the block 3 encodes not only the echo R message but also echo R2. Similarly, block 4 also encodes the echo R2 message. But as you can see, there is no overhead. We didn't have to send any additional blocks. So we get parallelism essentially for free. So, how does this all work together? What is our proposed block DAG framework? We run this on every server S. On the top we have a user issuing request for a protocol P. the user talks to a shim. The shim is instantiated with a protocol P. The shim passes the user request down to the gossip protocol. The gossip protocol writes the user request to the next available block. The gossip protocol also builds the block DAG. Therefore, it periodically sends and receives blocks over the network. But a correct server uses only received and valid blocks. We have seen the block DAG 2 slides before. Independently, the server reads the block DAG to interpret it. Here, the interpret protocol treats P completely as a black box. As we showed before, to simulate P, every server simulates the run of P for every other server. So when a server interprets a block DAG, it interprets every edge from block 1 to block 2 as messages from the creator of block 1 to the creator of block 2. And these messages are fed to the protocol P. Then P returns some messages. These are the messages to the next blocks. Eventually, the simulation of P finishes for server S. This is indicated to the shim, which passes the indication up to the user. So now, our main theorem. For every correct server, if a protocol P has some safety or liveness property, then shim P preserves this property. For the proof, we first show that a block DAG is actually a reliable point-to-point link between two correct servers. That is, messages interpreted on the block DAG have the properties of a reliable point-to-point link. So 1. Reliable delivery, 2. No duplication, and 3. Authenticity. The proof idea is that we then show that our block DAG framework only uses the protocol P as a black box. Every message transmitted by an execution of P is transmitted by the block DAG framework. So every property relying on properties of the reliable point-to-point links is preserved. For example, the properties of reliable broadcast. Some properties, e.g. related to performance, are not directly translating. We see that with the block DAG framework, we reduce the number of messages. Finally, in the background I talked briefly about DAG writer and narwhal and tasks as other block DAG based approaches. So while we are mainly focusing on correctness in our work, those protocols show that they are very efficient and even optimal. So, future work. I will highlight the two most fascinating ones. First, we could move from interpreting deterministic protocols to random protocols. Here there are two options. Option 1 is interesting if the protocol needs a randomized decision, for example, a coin flip. Then every server is going to flip a coin locally and writes the coin flip result in the block, as with a user request. Then every other server can replay the protocol with this additional information. Option 2 is interesting if we need unbiased randomness. We believe we can achieve this by incorporating a shared coin in a BFT setting as recently developed. Second, a major challenge is crash and recover and the reconfiguration of servers. In a way, block DAGs are very nice for this because you have this log. On the other hand, what and when can you garbage collect? How long has a block DAG to be kept? Similarly, how is the reconfiguration of servers handled? What happens when servers want to join or leave? Apart from splitting at predefined epochs. All these questions are important future questions and not necessarily limited to the block DAG approach. So, to recap, I have presented a framework to interpret a deterministic Byzantine fault-tolerant protocol embedded in a block DAG. We have shown that the block DAG essentially is a reliable point-to-point link, and we can use it to interpret the protocol on top of it, preserving safety and liveness properties relying on this point-to-point link. But what was the benefit? Why did we do this? So two main reasons are: one, we saw that we saved messages from actually being sent. We only ever send blocks over the network. The messages are left implicit, embedded in the block DAG. So we compress the messages to the point of emission. Second, we have one or even more protocol instances per block. So we can run many instances of the protocol in parallel, and essentially for free. With this, I thank you very much for your attention. If you have any feedback or questions, we are happy to hear from you. Thank you.